So what about any closed shell atom? Well, this gets intense because now, right, this could be applied to neon, argon, krypton, sodium plus, oxygen 2 minus, right? Any closed shell. And so by closed shell, right, we recognize that shell, for example, the K shell or the L shell or the M shell, right? The entire shell, if it's closed, if it's occupied by all electrons, it's going to have to be described by a spin correlated state. And this matrix gives us our only singlet possibility to describe that wave function. And it gets intense. So this is called the Slater Determinant. Okay. And so this is what's largely used in computation, right? In big molecular modeling or even atomic modeling. And you create this matrix by working your way through all of the number of electrons. So N is your number of electrons. So you'd work your way all the way over for that number of electrons, okay? And then the A's, B's, and Z's, let's see if I recall. Yes, so that's given just to help you keep organized for a given electron. So also the letters will give you the number of electrons so that you have a square matrix, okay? So this gets really intense, but that's why typically people use computers. You have to use a computer to do this. Okay, moving along. So now what happens to our orbital energy level diagrams? Okay, well, we start with this simple energy level diagram just describing level N. Okay, when we put in our subshells, right, S, P, D, and F, hopefully you remember for hydrogen and hydrogen only, each shell, right, end state, is degenerate, okay? And I'm not going to spend a whole lot of time with this because this is a largely review from your Chem 109. But when we start putting in multi-electron atoms, okay, we get an effective nuclear charge, okay, which is due to shielding of core and valence electrons, right? So for example, our core electrons way down here are going to shield the valence electrons way up here from the nuclear charge. So that means for multi-electron atoms, okay, the effective charge won't necessarily be the number of protons, all right? And a result of that is it splits the subshells. So subshells are split due to the shielding. And what ends up happening, the higher out you are in your subshell, the more shielded you are, so the less attraction you experience to the nucleus, which has a result of shifting their potential energies up. So for example, the 2p energy level gets shifted up slightly from the 2s level because it's not experiencing that full charge of the nucleus as much as it was if there was only one electron, okay? And so that splitting goes, hopefully you remember this, right, from the good old Gen Chem days and inorganic, right? S orbitals are less than energy than P, are less than D, are less than F, okay? So we see, right, 1s, 2s, and then we go to 2p, and then 3s, and then 3p, 3d, and then 4s, 4p, 4d, and then 5s, and so on. And also, if you recall, when we get into the really complicated atoms, levels like 3D and 4s, right, they can shift around depending on how many electrons you have in there. And I don't want to spend a lot of time getting into those details because I think that you've talked about that ample in your inorganic chemistry class, and that's talked about quite a bit in general chemistry. Okay, I just wanted you to give a little review, right? Remembering what happens to these orbital energy level diagrams for multi-electron atoms. Okay, and also remind you, we have to remember how to do electron configuration, because what's coming next are spectroscopic term symbols. And it's good to have a working knowledge of electron configuration to do your term symbols. So let's just review the simple atoms, okay? Lithium, beryllium, boron, etc. All right? So we remember that lithium is a 1s2 based on its position on the periodic table, okay? 1s2, 2s1. It probably would help if I put a periodic table right here. And so we can write that electron configuration, right, as 1s2, 2s1. And because we know that helium electron configuration is 1s2, we can use the condensed shorthand, right, by replacing 1s2 with helium, and that becomes helium 2s1. Okay? So, and then, of course, as we add more electrons, we keep populating those subshells. So I'll remind you, this is the Aufbau principle. When we have open spaces, our electrons will occupy those open spaces. So for example, when we go from boron to carbon, from 2p1 to 2p2, that last electron for carbon is not going to pair up. It's going to go into the open orbital to make the lowest energy configuration, right? So these are all ground states, okay? And when we go to nitrogen, we still have an open p subshell, so that electron will spread out into that open p subshell. Only then when we get to oxygen, where we no longer have any open subshells available, will electron pairing begin. And I always like to remind people, even you seniors, right? Oxygen is a di-radical. 2 unpaired electrons. That's why oxygen is extremely reactive. Okay. Fluorine only has 1 open electron, and then of course neon is a full closed shell. Okay. So don't forget about how to do your electron configuration. Okay, so just to remind you, Hund's rule says an electron in its ground state adopts an electron configuration with the greatest number of unpaired electrons. Oh my God, what did I say? I said Aufbau. Hund's rule. Let's erase that. The Aufbau principle is the building up, right? Putting electrons into each successive orbital. So Hund's rule says greatest number of unpaired electrons, okay?